A relation from set A to set B is the subset of A cross B. So R is the subset of A cross B. That's it. If A comma B belongs to R and B comma A belongs to R and A is equal to B, then it is called an anti-symmetric relation. A relation R on a set A is called equivalence relation if it is reflexive, symmetric and transitive. Hello dear students, welcome to this session of Discrete Mathematics class. I am Mr. Niranjan, Faculty, Department of Computer Science, Vidhyaashram First Grade College, the Temple of Excellence. Today in this session, I am going to take Unit 3, third unit in your Discrete Mathematics. So in this unit, we are going to study only the two concepts. The first one is the relation and second one is the graph. So relations and graph theory. Problems based on the graph theory. Now let me discuss regarding the relation. So in relation we are going to study regarding different types of relations and the problems based on those different types of relations. That's it. Now let us come to the first relation. Now before going to exact definition of a relation, let us know regarding the Cartesian product. In my previous classes we have discussed regarding the Cartesian product of two sets. Let me discuss once again regarding the Cartesian product of two sets. Now, suppose if A and B are any two non-empty sets, if A and B are any two non-empty sets, then the set of all ordered pairs x comma y, the set of all ordered pairs of the form x comma y, where x is an element of A and y is an element of B. That means first member is an element of A and second member is an element of B is called the Cartesian product of A and B. That is where x belongs to A and y belongs to B. This x belongs to A and y belongs to B. That means first member is an element of set A and second member is an element of set B. Then the product x comma y of the form x comma y is called the Cartesian product. Symbolically, the set A cross B is denoted as the Cartesian product of A and B is denoted as A cross B is equal to x comma y such that x belongs to A and y belongs to B. That is, A cross B is denoted as A cross B is equal to a set x comma y such that x belongs to A and y belongs to B. That means first member is an element of set A and second member is an element of set B. Then the ordered pairs x comma y is called the Cartesian product, Cartesian form. Now let us consider one example. Let me take if A is equal to 1, 2, 3, another set B is equal to 2, 3. Then the Cartesian product of these two sets is denoted as A cross B is equal to set of all ordered pairs. Let us take first one, 1, 2, 1, 3. Again second element 2, 2 and 2, 3. Then the third element 3, 2 and 3, 3. Okay. So this is called the ordered pair. Okay. Now, so A cross B is equal to 1, 2, 1, 3, 2, 2, 2, 3, 3, 2 and 3, 3. This is called the ordered pair. Okay. Now, ordered pair is nothing but set of all elements of the form x comma y such that x belongs to A and y belongs to B. Now, by knowing this ordered pair, let us discuss regarding the relation. What is the definition of a relation? Now, a relation is nothing but a subset of A cross B. A relation R is a subset of the Cartesian product A cross B. Suppose if A and B are any two non-empty sets, then the relation R from A to B is the subset of A cross B. That is, the subset of A cross B is the relation. Now, let us consider this example. If A is equal to 1, 2, 3, B is equal to 2, 3, if I take R is equal to, the elements R is equal to 1, 2, 1, 3, again 2, 3. These three elements, this is called the relation. So, since 1, 2, 1, 3 and 2, 3 are the elements of the set A cross B, therefore, this R is a subset of A cross B and this R is called the relation. And if you observe carefully, this relation is of the form R is equal to x comma y such that x is less than y. The first element is less than second element. See 1 comma 2, 1 comma 3, 2 comma 3. First element 1 is less than 2, 1 is less than 3, 2 is less than 3. So we can say this is a relation, and this R is the subset of A cross B. R is the subset of A cross B. Now you got an idea. So the relation R on A cross B is the subset of A cross B. So this is an example for the relation. Here what is the relation given? X comma y such that x is less than y from this A 1 comma 2 and 1 comma 3, again 2 comma 3 is the relation, and this R is the subset of A cross B. Now that is, suppose take one more example. If A is equal to x, y, z and B is equal to 4, 5, 6, then R is equal to x comma 4, y comma 5 and z comma 6. Thus this R is the subset of A cross B, then we can say that R is the relation. So if you write A cross B contains all the elements of this form: x comma 4, x comma 5, x comma 6, y comma 4, y comma 5, y comma 6, z comma 4, z comma 5 and z comma 6. In that x comma 4, y comma 5 and z comma 6 is a subset of A cross B. Therefore, this R is the subset of A cross B. Now you got an idea regarding the Cartesian product as well as the relation, right? Now let us come to the definition. A relation from a non-empty set A to non-empty set B is the subset of the Cartesian product of the set A cross B. A relation from set A to set B is the subset of A cross B. So R is the subset of A cross B. That's it. Now, so the subset is denoted by describing a relation between the first element and the second element of the ordered pairs and denoted as A comma B, A cross B. That means first element is an element of set A and the second member is an element of set B. The set of all first elements in a relation is called the domain. The set of all elements of the x comma y such that x belongs to A. The set of all elements of the relation R is called the domain, and the set of all second elements is called the image. That is called the images. That is called as the range. So therefore, the set of all first element is called the domain, and the set of all second element is called the range, and the set B itself is called the codomain. Okay. Now here, that is, the domain is nothing but set of all first elements of R. The set of all first elements of R is called the domain, and the set of all second elements of R is called as the range. That is called as the range. Domain and range. Okay. Now let us take for example, if R is equal to 1 comma 2, 1 comma 3, 1 comma 4 and 2 comma 3. If this is the relation, then what is the range, what is the domain of this? The domain of R is equal to set of all first elements of this 1 comma 2 is called the domain. And what is the range of R? The range of the relation R is equal to set of all second elements, that is 2, 3 and 4. This is called the range. That is the domain and range of the given function. Hope you followed. Okay. Suppose if a set A contains n number of elements, the number of elements set in A is m and the number of elements in set B is n, then the number of elements, the number of relations that can be formed from A to B, the number of relation is t to the power of mn. So the number of relations which can be formed from a set of elements m and n is 2 to the power of mn. That's it. Okay, this is a very important concept. Now let us come to the next concept. Let me take an example. If A is equal to 1, 2, 3 and B is equal to 5, 6, 7, then the relation R from the set A to set B is denoted by the arrow mark. So if this is, suppose if R is the relation, R is equal to 1 comma 5, 1 comma 7, 2 comma 7 and 3 comma 9. This relation is represented by a arrow diagram. A contains 1, 2, 3 and B contains 5, 6, 7. just 1 to 5, 1 to 5, again 1 to 7, again 2 to 7 and 3 to 9. This is the representation of a relation from in an arrow diagram. So, what is the domain? The set of all first elements, the domain of R is equal to set of all first element 1, 2 and 3. So, 1, 2 and 3, that is, this is the domain 1, 2, 3. And what is the range of R? Range of R is equal to set of all second elements 5, 7 and 5, 7 and 9. This is the second element 5, 7, 9 is the range. And what is the codomain? The set B itself is called the codomain. Codomain is equal to the set B, that is 5, 7 and 9. That's it. 5, 7 and 9 is the codomain. So, this is how we are going to find the domain and range for the given relation. So, here suppose if a set A contains 1, 2, 3, B contains 5, 7, 9 and these are represented by an arrow diagram. So, 1, 5, 1, 7, 2, 7 and 3, 9. So, the domain of this is 1, 2, 3 and the range is 5, 7, 9 and the codomain is equal to the set B itself 5, 7 and 9. So, the relation from set A to set B shown by the arrow diagram, the first component to the second components of all ordered pairs that belongs to R is represented by an arrow diagram. Now, let us come to the properties of relation. So, properties of relation, that is different types of relations. In different types of relations or properties of relations, we are going to study very important properties, that is reflexive property, symmetric property and transitive property. You might have been studied in your previous classes regarding reflexive, symmetric and transitive. Reflexive means reflect, A comma A belongs to R, same 1 comma 1, 2 comma 2, 3 comma 3, A comma A, B comma B, C comma C belongs to R is called a reflexive relation. Symmetric means if A comma B belongs to R implies B comma A also belongs to R. If 1 comma 2 belongs to R means 2 comma 1 also belongs to R, that is called the symmetric. And transitive property means if A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R. These are the three types of properties or types of relations. So, properties of relations, or it is also called as types of relation, the reflexive relation, symmetric relation and transitive relation. Now, let us discuss one by one. Now, reflexive relation. Reflexive relation means a relation R on a set A is called reflexive if A comma A belongs to R. If A comma A belongs to R, for all A belongs to A. For all A belongs to A, for all A belongs to A, if A comma A belongs to R, then R is called a reflexive property. R is said to be reflexive. A is related to A. Now, for example, assume a relation R is equal to A comma B. If A divides B on 1 comma 2 comma 3 4 is reflexive or not. So, A divides B. If A divides B, 1 divides 1, 1 divides 2, 1 divides 3, 1 divides 4, 2 divides 2, 2 divides 4, 3 divides 3, 4 divides 4. From this, whether we can say whether this relation is reflexive or not, check whether 1 comma 1, 2 comma 2, 3 comma 3 and 4 comma 4 belongs to the relation R 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4. So, 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4 all belongs to A. That is, for all A belongs to A, there exists A comma A belongs to R. A comma A belongs to R. That is, 1 comma 1 belongs to R and similarly 2 comma 2, 3 comma 3, 4 comma 4 all belongs to R. Therefore, R is reflexive. You can say R is reflexive. Reflexive property is said to be satisfied. Reflexive relation, R is said to be reflexive relation. So, if for all A belongs to A comma A belongs to R, then R is called as reflexive. 1 comma 1, 2 comma 2, 3 comma 3 and 4 comma 4 all belongs to the given relation, therefore it is reflexive. Let us come to the second one. Irreflexive relation means a relation R on a set A is called irreflexive if A comma A does not belongs to R for every A belongs to A. So, that is not reflexive. Irreflexive means it is not reflexive. If A comma A does not belongs to R, then it is called It is not a irreflexive relation. Now let us come to the second one, very, very important, symmetric relation. A relation R on a set A is called symmetric if B comma A belongs to R whenever A comma B belongs to R for all A comma B belongs to A. That is, for all A comma B belongs to A, if A comma B belongs to R implies B comma A also belongs to R. If A comma B belongs to R implies B comma A also belongs to R for all A comma B belongs to the set A. Then this is called a symmetric relation. If A comma B belongs to R implies B comma A also belongs to R. That is, if X comma Y belongs to R, if X comma Y belongs to R implies Y comma X also belongs to R, then R is called a symmetric relation. Now let us consider, for example, same example. In this relation, R is equal to 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 2 comma 2, 2 comma 4, 3 comma 3, 4 comma 4. Just whether it is symmetric or not. See here, 1 comma 2 belongs to R. 1 comma 2 belongs to R implies 2 comma 1. So in this set, 2 comma 1 does not belongs to R. Therefore, this is not a symmetric relation because 1 comma 2 belongs to the R, whereas 2 comma 1 does not belong to R. Therefore, this is not a symmetric. Even if I take 1 comma 3, 1 comma 3 belongs to R implies 3 comma 1 does not belongs to R. This is also not symmetric. Even 1 comma 4 belongs to R, 4 comma 1 does not belongs to R, 2 comma 4 belongs to R, 4 comma 2 does not belongs to R. So therefore, this is not an example for a symmetric relation. Now let us take an example on the symmetric relation. So if a relation R is equal to 1 comma 2, 1 comma 3, 2 comma 1, 3 comma 2 and 3 comma 1 and 2 comma 3. If you observe carefully, this is an example for a symmetric relation. Since 1 comma 2 belongs to R implies 2 comma 1 also belongs to R, 1 comma 3 belongs to R and 3 comma 1 also belongs to R, and 3 comma 2 belongs to R implies 2 comma 3 also belongs to R. This is just an example for a symmetric relation. So if the relation is like this, then we are going to call it as a symmetric relation. Here the condition A comma B belongs to R implies B comma A also belongs to R. Now let us come to anti-symmetric relation. A relation R in A is said to be anti-symmetric if A comma B belongs to R and B comma A belongs to R implies A is equal to B. Then that relation is called anti-symmetric relation. If A is equal to B, if A comma B belongs to R and B comma A belongs to R and A is equal to B, then it is called an anti-symmetric relation. That means, let us consider an example. If A is equal to 1, 2, 3, then the relation R is equal to 1 comma 1, 1 comma 2, 1 comma 3 and 3 comma 3. So if A comma B belongs to R and B comma A belongs to R implies A is equal to B, then such a relation is called as the anti-symmetric relation. Now let us come to the third one, very important one is transitive relation. So a relation R on a set A is called transitive relation if A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R if for all A, B, C belongs to A. So that is if for all A comma C comma belongs to the set A, then the relation if A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R, then such a relation is called as a transitive relation. Transitive. If X comma Y belongs to R and Y comma Z belongs to R implies X comma Z also belongs to R, then such a relation is called as a transitive relation. That is, if A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R. So let us consider an example. Let us consider an example. If A is equal to 1, 2, 3, 4, check whether the given relation R is equal to transitive or not. What is given? R is equal to 1 comma 2, 1 comma 3, 2 comma 2, 2 comma 3 and 3 comma 4. Let us take 1 comma 3 belongs to 1 comma 2 belongs to R, 1 comma 2 belongs to R and 2 comma 3 belongs to R implies, check whether 1 comma 3 also belongs to R or not? 1 comma 3 belongs to R. Since 1 comma 2 belongs to R and 2 comma 3 belongs to R, implies 1 comma 3 also belongs to R. This is called transitive property. Okay. So in general, if A comma B belongs to R and B comma C belongs to R, implies A comma C also belongs to R. That is called the transitive property. Now, let us come to a very important concept, equivalence relation. Now, equivalence relation. So, equivalence relation means a relation R on a set is called equivalence relation if it is reflexive, symmetric and transitive. If it satisfies all the three properties, reflexive property, symmetric property and transitive property, then such a relation is called as an equivalence relation. So, a relation is said to be equivalence relation if and only if it is reflexive, symmetric and transitive. If it is reflexive, symmetric and transitive, such a relation is called an equivalence relation. Now, let us take for example, let us consider an example. If A is equal to 1, 2, 3 and the relation R is defined by, R is given by R is equal to 1 comma 1, 1 comma 2, 1 comma 3, 2 comma 1, 2 comma 2, 2 comma 3, 3 comma 1, 3 comma 2, 3 comma 3 and 3, 4 comma 4. Check whether the given relation is an equivalence or not. Now, let us come to the first one, reflexive. Reflexive relation. What is reflexive? A comma H. See here, 1 comma 1 belongs to 2 comma 2, 3 comma 3, 4 comma. Since 1 comma 1 belongs to R, that is A comma A belongs to R, therefore R is reflexive. We can say R is reflexive because A comma A, B comma B, C comma C, 1 comma 1, 2 comma 2, 3 comma 3 are all belongs to the given relation, therefore R is reflexive. Now, second one, symmetric. Symmetric property, symmetric relation. What is symmetric relation? For all A comma B belongs to R, B comma A also belongs to R. See, here 1 comma 2 belongs to R, 1 comma 2 belongs to R implies 2 comma 1 also belongs to R. Okay. Further, if you take 1 comma 3, 1 comma 3 belongs to R implies 3 comma 1 also belongs to R. That is A comma B belongs to R implies B comma A also belongs to R. Therefore, R is symmetric relation. Symmetric property is satisfied. R is symmetric. Okay. Now, verify the last one, transitive. Transitive property, third one. Transitive. What is the condition for transitive? For all A comma B comma C belongs to R. If A comma B belongs to R and B comma C belongs to R, implies A comma C also belongs to R. Now, let us take here, let us take 1 comma 2 belongs to R, 1 comma 2 belongs to R and then 2 comma 3 belongs to R implies 1 comma 3 also belongs to R. 1 comma 3 also belongs to R. That is 1 comma 3 also belongs to R. So, therefore, what do you say? R is transitive. Now, you followed. So, R is reflexive, R is symmetric and R is transitive. That means, if R is reflexive, symmetric and transitive, then that relation R is called an equivalence relation. So, we can say that therefore, R is an equivalence relation. Equivalence relation. That's it. So, if it satisfies all the three conditions, three properties, such a relation is called an equivalence relation. Very important for the point of examination. Okay. Let us come to the next concept, inverse relation. Inverse. What is inverse relation? Let R be the binary relation from A to B, then the inverse of R can be defined by B comma A such that A comma B belongs to R. If A comma B belongs to R, then B comma A is called the inverse relation and it is denoted as R inverse. R inverse is equal to B comma A such that if A comma B belongs to R is called the inverse relation. Now, complementary relation means let R be a binary relation from A to B, then the complement of R can be defined by R is equal to A comma B such that A comma B belongs to R, that is A cross B minus R is called the complementary relation. Now let us come to the concept in detail, domain and range. As I told just now, the domain is nothing but the set of all first elements of the relation is called the domain, and the set of all second elements of the relation is called the range, and the set B itself is called the codomain. Now how to represent mathematically? So if there are two sets A and B and the relation R have an ordered pairs x comma y, if R is an ordered pair x comma y, then the domain of R is denoted as R is equal to a set X such that x comma y belongs to R for some y in B. So the domain is denoted as X such that x comma y belongs to R. Similarly, the range of R is denoted as y such that x comma y belongs to R for some x in. So the set of all first elements is called the domain. Domain is nothing but the first elements of the relation is called the domain, and the second element, set of all second elements are called as the range of R, and the set B itself is called the codomain. Now let us take an example. Let A is equal to 1, 2, 9 and B is equal to 1, 3, 7. Then if the relation R is equal to, let us come to the case 1 first. The relation R is equal to is given by 1 comma 1 and 3 comma 3. Now what is the domain of this? The domain of this relation is the set of all first elements 1 comma 3 is the domain. And what is the range? Set of all second elements, that is also equal to 1 comma 3. So domain is nothing but the set of all first elements and the range is the second element. So the domain is 1 comma 3 and the range is 1 comma 3. Now let us come to the case 2, second example. If the relation R is defined as less than, here x is equal to y, here x is less than y, 1 comma 3, 1 comma 7, 2 comma 3 and 2 comma 7. Now what is the domain here? Domain is the set of all first elements 1 and 2. Domain is 1 comma 2. And the range is nothing but set of all second elements 3 and 7. 3 comma 7 are the second elements. Now whether is this reflexive? This is not reflexive. 1 comma 1, 2 comma 2, 3 comma 3 does not belongs to R. Symmetric, this is not symmetric. 1 comma 3 is there, 3 comma 1 is not there. And if you want to check transitive, 1 comma 3 is there and you can't take, this is not an example for reflexive, symmetric and transitive. Let me take one more example. On the set of triangles, a relation is defined by R is equal to T1 comma T2 such that T1 is similar to T2. Now let us come to the first property, reflexive. What is reflexive? A comma A belongs to R. If A comma A belongs to R, for all A belongs to the set A. Now here verify, since T1 comma T1 belongs to R, that means every triangle is similar to itself. T1 is similar to T1. Every triangle is similar to itself. Therefore, it is reflexive. So R is reflexive. Right. Second, symmetric. Check the symmetric relation. What is symmetric relation? For all A comma B belongs to R, if A comma B belongs to R implies B comma A belongs to R for all A comma B belongs to A. Now, if T1 is similar to T2, implies T2 is also similar to T1. That is, if T1 is similar to T2, implies triangle T2 is similar to T1. That is a symmetric relation. Now let us come to the third one, transitive relation. Transitive relation. If for all A comma B comma C, let us consider if for all triangles T1, T2 and T3 belongs to A, T1 comma T2 belongs to R and T2 comma T3 belongs to R, implies T1 comma T3 also belongs to R, because T1 is similar to T2 and T2 is similar to T3, implies T1 is also similar to T3. See, suppose if there are three triangles, triangle 1, triangle 2 and triangle 3, if this is similar to this, then T2 is similar to T3, implies T1 is also similar to T3. This is how we can verify the equivalence. So, since R is reflexive, symmetric and transitive, therefore we can say that R is an equivalence relation. Equivalence relation. So, that means the set of all triangles in a plane, so that E similar to E is an example for an equivalence relation. That's it. Okay. This is how we are going to verify the properties of relations like reflexive, symmetric and transitive. Hope you followed. That's all regarding this session. Let us meet with the different concept in the next session. Thank you. Thank you very much.